welcome back. In this video I'll talk about donuts. Yeah, it was actually requested, but I'm going to talk about Tauruses instead. I want to please you guys, so I'm open for the craziest of topics, but anyway. So an ordinary Torus is a surface having genus 1, or Euler characteristic 0, and therefore possessing a single hole. And the single-holed ring torus is known in older literature as an anchor ring. It can be constructed from a rectangle by gluing both pairs of opposite edges together with no twists. And the usual torus embedded in three-dimensional space is shaped like a donut, which is quite funny, but the concept of a torus is extremely useful in higher dimensional space as well. In general, Tori can have multiple holes, with the term n-torus used for a torus with n holes. The special case of a two-torus is sometimes called the double torus, the three-torus is called the triple torus, and the usual single-holed torus is then called the or a torus. A second definition of n-tori relates to dimensionality. In one dimension, a line bends into circle, giving the one torus. In two dimensions, a rectangle wraps to a usual torus, also called the two torus. In three dimensions, the cube wraps to form a three manifold, or three torus. In each case, the n torus is an object that exists in dimensions n plus 1. Integrals of motion lie on the n-dimensional manifolds, which is topologically equivalent to an n torus. Torus coloring of an ordinary one-hole torus requires 7 colors, consistent with the He-Wood conjecture. Let the radius from the center of the hole to the center of the torus tube be C, and the radius of the tube be A. Then the equation in Cartesian coordinates for torus, azimuthally symmetric from the z-axis, is parentheses C minus the square root of x squared plus y squared all squared plus z squared equals a squared. And the parametric equations are x equals parentheses c plus a cosine v all times cosine u, y equals c plus a cosine v sine u, and z equals a times sine v. For u and v, an element of the interval 0 to 2 pi, where 2 pi is not included. 3 types of torus, known as the Standard Tori, are possible depending on the relative sizes of A and C, where C is greater than A, corresponds to the ring torus, and C equal to A corresponds to the horn torus, which is tangent to itself at a point 000, and C less than A corresponds to the self-intersecting spindle torus. If no specification is made, torus is taken to mean ring torus. I'm actually going to illustrate these Standard Tori, where the first image shows the full torus, the second a cutaway of the bottom half, and the third a cross-section of a plane passing through the x-axis. So in general, the ring torus is this narrow guy that has no friends. The horn torus is that middle guy that, follows along. And then we have the spindle torus, which is really fat and, no comments. And the Standard Tori and their inversions are cyclides. And if the coefficient of sine v in the formula for z, which I'm going to discuss below. So enjoy. So, to compute the metric properties of the ring torus, define the inner and outer radii by r is congruent to c minus a and capital R is congruent to c plus a. Solving for a and c gives a equals 1/2 times parentheses capital R minus r and c equals 1/2 capital R plus r. And then the surface area of this torus is S equals parentheses 2 pi a times parentheses 2 pi c. And this simplifies to 4 pi squared ac, which is also equal to pi squared times parentheses capital R plus r times parentheses capital R minus r. And the volume can be computed by Pappus centroid theorem. And it becomes v equals parentheses pi a squared times parentheses 2 pi c, which simplifies to 2 pi squared a squared c, which simplifies to 1/4. I don't know if I can say simplifies, but 1/4 pi squared times parentheses capital R plus r times parentheses capital R minus r squared. And the volume can also be found by integrating the Jacobian computed from the parametric equations of the solid. So, as I said before, they become this, which simplifies to J equals, we all know the definition of the Jacobian, of course. And this is going to equal r prime times parentheses c plus r prime cosine v, giving v equals the integral from 0 to 2 pi, integral from 0 to 2 pi, integral from 0 to a, r prime parentheses c plus r prime cosine v, dr prime du dv, which is equal, again, to 2 pi squared a squared c. Yeah, as before. And the moment of inertia tensor of the solid torus with mass m is given by I equals, and then the matrix 5/8 a squared plus 1/2 c squared times m 0 0 0 5/8 a squared plus 1/2 c squared m 0 0 0 3/4 a squared plus c squared m. And the coefficients of the first fundamental form are capital E equals parentheses c plus a cosine v squared, f equals 0, g equals a squared. And the coefficients of second fundamental form are e equals minus parentheses c plus a cosine v, all times cosine v, f equals 0, and g equals minus a. Giving Riemannian metric, the s squared equals c plus a cosine v squared du squared plus a squared dv squared. And the area element, dA equals a parentheses c plus a cosine v du wedge product dv. And Gaussian and mean curvature as k equals cosine v over a parentheses c plus a cosine v, and h equals minus c plus 2a cosine v all over 2a parentheses c plus a cosine v. A torus with a hole in its surface can be turned inside out to yield an identical torus. A torus can be knotted externally or internally, but not both. These two cases are ambient isotopies, but not regular isotopies. There are therefore 3 possible ways of embedding a torus with 0 or 1 knot. For one arbitrary point P on a torus, not lying in the xy plane, it can have 4 circles drawn through it. And the first circle is in the plane of the torus, and the second is perpendicular to it. The third and fourth circles are called, sorry for my pronunciation, I don't know, Villarquier circles. Yeah, I think that was all. So don't underestimate donuts, it can be quite complicated. But anyway, thank you for watching, have a nice day.